Today we'll start at number 19 where we left off. And so we're going to do a missing values analysis. So on this, probably the easiest way, as far as if you look at the assignment itself, it's just looking for the percent missing across all these different variables. Well, is.NA is a logical test that just looks for whether or not something is a missing value. So if you run your data frame through is.NA, it's going to put out a bunch of trues and falses going across each of your variables, and it's just telling you, going down income 3, like these are not NA, this one is, etc., etc. Now, whenever you see Boolean logic, if that's treated as numeric, then false is 0 and true is 1. So if we have all trues and falses in these columns, and basically think of that as all zeros and ones, then if you take that and average across that, if half of your values are missing, then half of those are going to be ones and half are going to be zeros. When you take the average of all those ones and zeros, it's going to come to 0.5. And so you'll know you've got 50% missing there. So what we can do is take our is.NA and take the means of all these columns of trues and falses. So we'll wrap that in call means. And now it will give us the means of each of those things. And if you want to do it straight to a percent, then all you have to do is multiply it by 100. And now we have the actual percents for our missing variables. So we're missing 13% of father education. We're missing 1.6% of GPA 1. Now, here in a minute, I'm going to copy and paste a big chunk of code that just, again, here's how you could take it and make it output a thing that would be easy, just a straight copy and paste. But I don't want y'all to waste your time sitting here and typing in this big chunk of code. So I can just send out that part of the code later on. But basically, so as we're looking through our missing values, what is it that we're actually looking for in terms of like limits of missingness, and like what should we consider when we look at missing values and thinking about whether or not it's problematic and we need to do something about it?
Maybe the time when the data was collected. So I would expect more missing values at time 3 than time 1.
Right. So maybe missing more values at time 3 than time 1 simply because of attrition. Also, if we look at our time 3 variables, if we have income, it would make sense that would be missing a little bit more at time 3, because how many people don't have a job, thus they have no income, no job score, no job stat, because maybe they're still in school, maybe they're disabled, or whatever the case may be. So that there's a logical reason that you might be missing some of those values. What about like father education missing 13%? Is like what might you think about why that's missing so much?
They didn't know their father's education?
There might just be a large percentage of people who don't know their father, and so it's not that it's missing because they didn't answer it. It's missing because they don't know.
I really want to make a Star Wars joke right now, but I'm going to refrain.
I have a quick question. It might be kind of a stupid question, but when you see these percents right here, can you just multiply it by your observations to determine how many actual missing cases there are for that variable? Or
that's what this is.
Well, this is percent, but not ends. He's right. And in the homework, I do ask for n and percent.
Not on this table.
Anymore?
That's on the first table that we did.
Great.
That was just the frequency table. For this one, I mean, yeah, in theory you could. See, but we already have. If you look on that first frequency table that we did, where we have that valid percent, we have the ends and the valid percent, so you could figure out that number using that as well.
okay.
But yeah, so the point is that as we're looking across these things, like things missing isn't inherently a problem that you have to do something about. You have to think about what things do we want to try to reduce the missingness of. So in this case, if anything is missing less than, say 5%, like not really that much of a concern. So when we look across all of these, the only things that are missing more than 5% that aren't one of the more or less explainable things are those SMA and SRA scores, those math achievement and reading achievement scores. So what we want to do now is look at, does the missingness of SMA and SRA, is that related to any of our variables or any of the variables in the data set systematically, or is it missing at random? So
Can I pause you for just a second? Okay, so I want to just make sure that we're all clear on what's going on here. The very last part of our homework assignment is going to talk about missing data. We're going to be looking at patterns, and we're going to be doing imputation if it's warranted. And so what we just did right now was to say, are there candidate variables for imputation? What defines a candidate variable? Austin just mentioned two things. What were they? Missing at less than 5%?
Oh, greater than 5%.
Right, so if more than 5%, then potentially that's a candidate variable, unless what?
Systematically related to.
That's what we're going to decide. We don't actually know if anything is systematically related yet. That's the next step.
If you can explain it for some reason, like people are unemployed and don't know your dad.
Right, so if there's a logical reason why the data are missing at greater than 5%, probably imputation doesn't make sense. You wouldn't impute values of income for people who don't have jobs, right? So it makes sense to not impute or try to impute father education for people who didn't know their dads, right? Or weren't able to report on that. So really missing values imputation makes sense if A, there's enough of it that you should worry about. Otherwise, it really doesn't matter what you do with it. You're not either losing a lot of data, or you can use almost any technique, including a mean substitution, and be fine. Unless you have a reason not to impute, because the data are missing in a way that makes sense to you from your kind of theoretical or methodological perspective. So when we looked at the percentages, can we pull those back up for a moment? I think Linda was the first one to say time 3 variables missing at greater than 5% might make sense for reasons like either attrition or because not everybody has a job and they can't report on their job satisfaction if they don't have a job, right? But if we look at the time 1 variables, which ones seem like they have, well, first let's start with which ones are greater than 5% missing of our time 1 variables. Say it. SMA is at what?
10.85.
Yeah, 10.8%. So that's above our threshold. What else is missing at greater than 5 at time 1? Father ad's at 13%. SRA is at 9.9%. Mother ed's at 7.3%. That's at time 3 though. There's a 3 at the end of it, so that's a time 3 variable. So at least from time 1, we've got education of the parents and standardized math and reading scores in middle school. Okay. We've already decided, I think, that imputing education for parents might not make sense. Why do you think there might be so much data missing on standardized math and reading?
Administration error.
Say more.
Just like when they're administering whichever test, they did something incorrect.
Okay, yeah, these are actually pulled from school records. So they might not have been there that day. I mean, my kids do MAPS testing. You guys did all the testing. Maybe you were sick that day and you didn't get the score that year, right? So, but we don't think that it's probably like there was a scandal in, I think it was Texas, where like the principal told all the dumb kids to stay home on, this is really insensitive of me to say, but the less well-performing kids to stay home on testing day because they didn't want to bring down their school score. We don't think that's what's happening here. And so we don't have any reason to assume on the front end that there's anything systematic about why math and reading might be missing for some kids, other than maybe they were just sick the day that happened to be given that year. So they are good candidates for imputation because they're missing it greater than 5%. We can't think of a reasonable reason why they would be and why it would be a problem to then estimate it. And so the next step where we're going is to say, okay, if we are interested in imputing a value for these variables where we're missing some data, the first thing we need to find out is if we are in the MCAR, missing completely at random, missing at random or MAR, or the NMAR, not missing at random. Is there something systematic about the missingness? For example, is it really that the lower performing kids were told to stay home? We're going to find that out. Okay. So before you do any imputation, you first want to know, where are your missing data? Are they random, or is there something systematic? And that's what we're going to do now.
All right, and real quick before we go on to that, this is that chunk that I was telling you about, and this is why I don't want to sit and wait for everybody to type it out. But basically all I'm doing is I'm taking the names in the order that they're on the homework and just storing that as a thing called misnames. And then make a table where the variable name is the column name from the data frame. Miss.pct, the missing percent, is that same thing from here. I just put it down here. So that will create a table that has the column name beside the percent. And then using filter and filtering to where variable is in this thing. So because we have all those extra variables in the data set. And so this will take it down to just the ones that we're interested in and pipe that straight into a CSV. So again, I will send out this code or something like that. We'll
did create a Word document on Box so that people could.
And I just recently found, and I will experiment with, there's a package that I just discovered from the ARC conference called Live Code that basically allows me to run some stuff, and it creates like a local server on the Wi-Fi network that would make it to where y'all just type in an IP address and go into Chrome, and whatever I'm typing can pop up in real time on your browsers and such. So I'm going to play with that. I'm just not sure if that will interfere with other things that we're doing, so I'm looking into it a little bit more, but in the future that might be an option as well. So now down here at 21, so we want to look at imputing SMA and SRA, but like she was saying, first we have to see if there's any systematic relationships between its missingness and all our other variables. So we'll start by creating a dummy coded variable for whether or not each of these variables is missing. And then we'll treat that dichotomous variable. We will look across our variables like sex, birth region, English, the education stuff, look across all these variables using either a t-test if it's some continuous thing or a chi-square test if it's a categorical thing. And then if it's significant, then that tells us hey, there's something systematically related between missing values and this particular variable. Whereas if it's not significantly related, then we feel more confident that it's missing at random. Because we are about to run 22 different analyses, we need to control for that family-wise error by using some sort of correction. In this case, we'll use the Bonferroni correction, which is just where you divide your alpha by the number of tests that you're doing, and then that's the value that you compare it against. So in this case, this is another one of the sections where we'll start, but actually doing it, you'll have to finish it after class because it's just going to be writing a lot of lines for a bunch of different t-tests and chi-squares, but we'll at least go over how to do one of each. So the first thing that we need to do, again, is dummy code a variable about whether or not it's missing. So we'll start with taking our data frame and mutating it to create a new variable. We'll call it SMA missing. And here we'll just use a simple if-else. So if-else is.na for SMA. So if SMA is NA, then code it as, well, rather, if is NA SMA is true, then we'll code that as 0. So if it's missing, code it as 0. If it's not, code it as 1. Come down to the next line and do the same thing for SRA.
So 1 means that it is missing, or 1 means that it's not missing?
1 means that it is not missing. Because is NA, if that is true, if it is NA, the output is 0.
Okay.
If it is not NA, the output is 1.
Normally we do it the other way, because 1 is usually true, right, and 0 is usually false. Is that right?
If, yes, and
So what you're saying is SMA missing? 1 would be yes, true, it's missing.
right, so is NA, if that's true, if
And
it
we
isn't
normally
NA
wanna-
value, if it's NA, then we want it to be
1. And if it's actually present, we want it to be 0.
It could go either way. The reason I do it as like 0 means like it is not here. 1 means like yes, it is here. Is like the way that I have it. It doesn't matter.
Mhm.
Either way, all it's going to do is reverse the sign of your t-test or chi-square. So whichever way works for you. If we wanted to do it the other way, we could.
Is it conventional to do it the other way?
So it sort of depends on what you're calling your variable and what you want it to represent. So when I call it SMA missing, I'm asking like, is this variable missing? And if it's 1, it's like, yeah, I'm missing. But I think it's okay, or you could say SMA present, right? Or SMA is like a value. So it doesn't really matter how you do it. I mean, Austin is right. But just my personal convention has just been that if I'm coding for missingness, 1 means it's missing, and 0 means it's not, but I'm totally fine with us doing it as like 0 means I don't have this value, and 1 means I have a value. As long as you're clear on how we coded it and what it means.
Yeah, and this is just my personal convention, and some things are just personal conventions. There is no like good versus bad practice. It's 6 of one, half dozen of the other. And this is one of those cases. Sometimes the personal conventions are rooted in there's a specific way to do it this way, but in this case, it doesn't really matter. But either way, so now we have coded SMA and SRA missing. So with the way that I have it coded, like this one is there in both of them, and this one is missing them. I don't know if we have any that's missing one but not the other.
We do have some.
Well, not on the screen, but either way. So now that we've done that, you got to remember to store it back into your data frame. And so now we have those 2 new variables. And so now what we got to do is all those t-tests or chi-square tests. So we'll start with using an example of SMA and one of our chi-square tests, which will be when we're looking at that broken down across our categorical variables. So for instance, sex. Let's see if one sex or the other is systematically missing more. So to do the chi-square test, the function is called chi-square test, and all you have to do is give it your 2 variables. So we'll say df $sex, comma, df $SMA missing. And this will perform a chi-square test across these variables. And when we run that, like here's our chi-square statistic, degrees of freedom, and our p-value, and we see that it is not significantly related to sex. So it seems that men or women are not more likely to be missing SMA than the other gender.
And so let me again pause for a moment. What we're basically doing here is taking a dichotomous variable, missing or not, and looking at its relation to other variables. If they're categorical variables in our data, like sex, then we're going to run chi-squares. If they're continuous variables like age, we're going to run t-tests, which are basically just comparing 2 groups on a continuous variable to see if the means are different. If, in this case, what do you think we're hoping for? We're definitely hoping that things are not significantly related. We would love to be in, as far as we can tell, the data are missing at random. We can't find any reason, rhyme or reason for why Johnny's missing, but Susie's not. Yeah.
Sorry, I have a weird error message.
So if it's missing at random, then you can impute, basically, is the.
Yeah, if it's missing at random, most of the imputation techniques will be fine, almost all of them. Missing like multiple imputation or expectation maximization or even regression imputation. If it's missing systematically, which we may encounter that today, then we're going to talk about how to deal with that. But as I said in lecture, systematically missing data are more problematic if you ignore that they're systematic, and you need to somehow model the systematic nature of it. So I described for you the time when all my people, certain people wouldn't finish a study that involved looking at images of pornography, and that it was systematically missing based on sexual disgust scores. So I couldn't ignore that. I couldn't just impute their values. I had to recognize that there was something about it. I want to say one other thing about this. When you're evaluating your p-values, remember that we're evaluating it based on the Bonferroni corrected p-value, not conventional 0.05. Because if you're looking at the systematically missing nature of your data, you're going to be running a ton of tests. In this case, we're probably doing
22.
Well, we are doing 22. Okay. And so because we're doing 22 of them, we divide our conventional alpha, 0.05, by the number of tests we're doing, 22. So the p-value for systematically related to this variable is not going to be 0.05, less than 0.05, it's going to be less than 0.002. Okay? So keep that in mind as you're doing your assignment.
I have a question about like figuring out what p-value you need to divide by. So would you do that separately, like the number of tests, like for SMA and SRA, like are we doing 22 separate tests?
No, that's, well, and it'll make more sense once we get through, because I was going to talk about the p adjustments after we looked at how to do the actual chi-squares and t-tests. So I'll come back to that point.
Okay. Just wanted to be clear because the first p-value meets conventional criteria, so I didn't want you to get confused and think always it's 0.05. Thank you.
So after, so that's how we do the chi-square, and then for the t-test, it's going to be similar, only now instead of having the comma, let's look at, say log friends 1 of our continuous variables. So we'll use t-test, df $ log friends 1, and then instead of a comma between them, in this case you use a tilde, and it's a formulaic approach. So you could think of this verbally as kind of like, friends 1 regressed on, SMA, but when it's wrapped in that t-test function, it'll be the same thing. So df $ log friends 1 tilde df $ SMA missing. And when we run that, it now gives us our t-test results. We can look at our t-statistic, our degrees of freedom, our p-value here. And then, so now let's just imagine that we copy and paste this, a bunch of times, and for all of them, for SMA missing, we have, chi-squares for birth region, for English, fatherhood, et cetera, et cetera, et cetera. And then we have t-tests for our GPA, depression scores, all that sort of stuff. So we have 11 chi-squares or t-tests for SMA missing. And then we copy and paste all of those and change SMA missing to SRA missing. And so now we've run across, we have our p-values, we jot those down for all 22 of our things. Now this is where now we would look at those and say, okay, we've now done 22 analyses, so we need to adjust that p-value. And Anna's convention is to use the Bonferroni correction, and so in that case we have 22 analyses, divide 0.05 by 22, so now 0.002 is our thing. So we look at all of the p-values of all 22 chi-squares and t-tests, and if any are less than 0.002, now we say that it's significant. Bonferroni isn't the only correction for p-values. I personally prefer the Bonferroni home correction, which is a little less conservative than Bonferroni, which it basically, instead of dividing everything by 22, if you order all your p-values in ascending order, you divide the first one, you compare it to your number of tests, or your alpha divided by your number of tests. So that first p-value is compared against 0.002. That second smallest p-value is corrected against 22, or 0.05 divided by 21. The next one is 0.05 divided by 20. And so with each correction, there's an adjustment for what it's made. So it's not just comparing everything to 0.002. But the way that it works out, because it's in ascending order, that at some point you're going to get to where the p-value is already bigger than whatever the correction level is, and you know that nothing below that is going to meet that criteria. Like I said, you'll just redo this over and over and over for now. There are functions that do this sort of thing. We're not going to go over it though. Just know that it's out there, and we can talk about that later. So as far as for the assignment, you'll go through and you'll pull out all of those t-statistics or chi-square statistics and those p-values, and then like I said, you compare against 0.002 and see if any of them are significant.
So we don't, just compare all those p-values to that 0.002.
Mm-hmm.
Yeah, we're gonna just use a standard Bonferroni.
Okay. I didn't know if there was a function.
Yep, like because you just manually, there are functions that do Bonferroni like p adjustments, where instead of just calculating the p number that you're computing or testing the raw p-value against, it will actually convert that p-value using a Bonferroni correction. And if you wanted to do that, you could just make concatenate all your p-values and run it through a p-adjust function, and it will adjust those, and then you can see are any of them below 0.05. But I don't want to confuse people, so this way is the most simple and straightforward. Run a bunch of t-tests, run a bunch of chi-squareds, do the math, and compare your p-values against that value. So then that brings us to number 23. And we'll just assume, I'll let y'all figure out after class when you're doing the assignment, but we'll just assume that there is no systematic relationships, that everything, it seems to be missing at random. And so now what we want to do is we want to impute the missing values for SMA and SRA. There are tons of different ways to impute data. There's a package called MICE. It's multiple imputations of chained equations, and it's a really awesome and incredibly powerful package. It's what I prefer to use for imputations, but there's a lot more to it. So today we're going to stick with the simple regression-based imputation. So if we have our math achievement and our reading achievement, we have other variables in our data set that could logically, you could make an argument for saying this is probably a pretty good predictor of our missing variables. You know, for instance, if you have somebody's GPA and their math achievement, you can probably pretty closely approximate what their reading achievement is, or vice versa.
Did you want to pull up that correlation table that we did the last time too? Because I think that would be a good place to, yeah. You had shown us a really pretty one, I think, in GG plot with
Oh, the performance analytics.
oh yeah, that was so pretty. Okay, so just to pause again and kind of reorient everybody here. What we let's assume for the moment that you've done all of your t-tests and your chi-square analyses and you're finding there's nothing systematic about your missingness on the two variables you want to do some imputation for, reading achievement and math achievement. So the next thing we have to do with them is decide, okay, what are we going to do to decide how to guess, right? What's going to be our best guess about reading and math achievement for the kids who don't have those scores in there? And a good place to start for regression imputation, as Austin mentioned, there are better methods, but given that there's nothing systematic about these data missing, this is okay, is to look at your correlations and say, okay, well, in the variables that I have available to me, what are the best predictors? What are the highest associated variables that I could potentially throw into a regression in order to make a best educated guess about the missing data points? And that's why it's good to refer back to your correlation table, look specifically at the SMA and the SRA, and take a look at what correlations and what potential variables might be good candidates.
Is this part conceptual too?
It is conceptual, but you should also be data driven, because in the end you want the best predictor even if you have no idea why it's like that. So, or even if you don't like that it's like that. So let me throw something out there. Let's assume that reading is higher in girls than in boys. And you're like, well, the feminist part of me says that's a bunch of BS, whatever. But if that's how your data, or your data is saying like that matters, then you might want to take a look at that. Okay.
All right, so basically what we're going to do is we're going to do a couple of linear regressions, and we will regress SMA on SRA and GPA, and then regress SRA on SMA and GPA. Before we can do that, like for the purposes of these regressions, we still need to fill those currently missing values with something, and the mean is better than nothing. So the first thing that we're going to do is take all of those or take these two, or all three of these variables, and just mean fill those things. Well, there is so we're going to pipe our data frame into a mutate to create some new variables. And I'm just going to call it SMA.imp, which is my way of saying like this is just like a real basic mean imputed SRA. And then there is a function in the impute TS package. And the function that we're looking for is this NA mean. And what NA mean does is whatever you put in it, in this case, since we're doing SMA, we want to do the NA mean for SMA. And so now what this will do is it will create a variable called SMA.imp that it just takes SMA, and anywhere that there's an NA value, it puts in the mean for SMA for it. And then we'll do the same thing for SRA.
So if you were just doing mean imputation period, this you could stop here, and then you would have your imputed values. That's not what we're going to do. If you were just doing a mean imputation, so filling in missing values with just the mean of the variable,
I got you.
this would be enough. But that's kind of a more dumbass way to do it. So it's a first step for us in what will eventually be our regression. But for now, that's the first step.
Why do you have a period, an NA dot period and an NA underscore? Does it matter?
Because I had a typo.
Oh, I thought maybe it was like.
Should be NA underscore mean. I would have figured that out as soon as I tried to run it, but. All right, so now basically we've just created these three new variables, but I haven't stored it back to the data set yet. But again, all it's doing is where there are missing values in SMA, it's putting in the mean of SMA, or the mean of SRA, or the mean of GPA1. So now come back reassign that to our data frame.
So in mine, when I pull up that, it pops up with the NA, oh, never mind.
What? Oh, wait. Mine says there's no package called in.
Yeah, you gotta install it.
Yeah, if you just, you can either go up to like tools and install package, look for impute TS, or use install.packages and impute TS. Let's see, is there another question?
Same thing.
Oh. So now that we have our three, there are no missing values in these three variables that we just created. So those are the ones that we're going to use in our regressions. And we're going to need to do 2 regressions. One, we're going to make a model for SMA. One, we're going to make a model for SRA. So let's start with our SMA model. And my convention is like all models start with.
Can you pause for a second? I can't find the package. Not sure why.
I did that and I accidentally put input.
Oh, there it is. I found it.
My naming conventions for models is that models always start with mod, and it's either like mod dot something or mod 1, mod 2, mod 3, etc. So again, this is just my convention. So if we're going to do mod SMA, and to create a linear model, the function is lm. And in lm, we just tell it, we give it a formula for what we're regressing on what combination of things and a data frame. So we'll say we want to regress SMA.imp. Tilde is, again, that formula for regressing on. And we will regress that on SRA.imp and GPA.imp. And it would help if you also tell it where the data is. Data equals df. So now we've created this model for our SMA, and we'll do the same thing for SRA. Only change it here, here, and here. So we've now created our 2 linear models that we are predicting, the SMA based on their SRA and their GPA, or predicting their SRA based on their SMA and GPA. So now there is another function, like we want to see what are their predicted values. For that, the function is conveniently called predict. So if all we do is we run predict mod SMA, the output will be all of our predicted values for each participant. Same thing if we run predict mod SRA. We can see those actual predicted values. So now if we wanted to look at, say, the correlations between our predicted values of SMA and the actual values of SMA, we could take our predicted values here and we'll wrap it in core, our correlation. We want a correlation between our predicted values and our original SMA. And then with core, because there are missing values, we have to tell it to do something with the NAs, or it's going to pop up and give us an error. So we can just say use equals pair. And that's just saying to use the pairwise complete observations. And when we run that, we can see the correlation between our predicted values and the original values is 0.67. And then we could do that same thing for mod SRA and go on from there. Do you wanna speak to that before we move on to then how to actually?
Yes. So let me just pause and explain to you why we're doing what we're doing, because we're doing a lot of things, but I keep wanting to bring you back to like what's the purpose of all this, okay? First of all, does everybody understand why we started by imputing the mean? Does anybody, okay, tell me why. Why did we start by imputing the mean?
Get rid of the NAs.
Okay, and why would we want to get rid of the NAs?
Just making a more smooth process when running the regressions.
What happens if we were to try to estimate missing values and we still had those values missing?
The model wouldn't run.
It wouldn't run for, unless we specify it, but it wouldn't run for those values. So we actually kind of needed to start by giving it something so that then it could run to give it a new predicted value. So if we had originally not imputed the mean, and then we had run our regression, then what it would do is it would basically either not run, or if we specified to eliminate the missing value pieces and just ignore them, it would give us predicted new values in our regression, but only for people who already had data. We're like, that doesn't help us. We need data for the people who don't have data. And so in order to get them into the regression in the first place, that's why we gave them a mean. Does that make sense? We're doing basically what the missing values packages do by themselves behind the scenes, but we're doing it explicitly step by step. Okay? So we gotta start by giving them something. And the something we can give them is our best guess, which absent any other information is the mean. By giving them a mean value if they were originally missing, we can now give a predicted value. Okay, so originally they were missing, but now they're included in our regression, meaning they're gonna get a predicted value. So let's say for case 917, can you point to 917 for a moment? Right there, 917. Let's say for the moment that 917 was actually missing. And if we had not estimated, or if we had not put in the mean, 917 would not get a missing values or a predicted value in this regression, because they never would have been part of the regression. They would have been cut off from the regression. By now including them in the regression, they don't have a mean score for this. They now have a best guess score based on all the other 2,000 people. And so instead of using the mean of say it's 50, because that's about right average on an achievement test, instead of giving them a 50, we now have a better guess about what they actually should have gotten, which is 41.5. So by first including the mean, we allowed them to be part of the regression, which meant they now got a predicted value. And the next thing we're going to be doing is filling in into the original variables the predicted values that were originally missing. Okay. So if the person had their score, we're not going to override it. But if they didn't have their score, we now have a better guess about what they should have gotten. Does that make sense to everybody so far? Okay. What the correlation is doing is I want to, again, everything that we're doing in this class is like, let's do a thing now, let's pause and let's think about the thing that we did. So for example, when we did our transformations, I had you transform it, but then I had you correlate the transformation to the original variable. Nowhere does that actually need to happen. The only reason I wanted you to do that is because I want you to get comfortable with what does that mean? How close or how far from the original data am I if I fuck around with my variables like this? And so the same thing is true here. What I'm wanting you to do is say, okay, you just predicted. How close were your predictions? How good of a job did you do in overall, right? Not for the missing people, just overall. We are then going to go back and take a look at what happens once we put in the missing values. But for now, I just want to say, how good is your regression? Is it a shitty regression? This case, a correlation of what is it, 0.6 something?
0.67.
That's pretty good, right? That the best guess versus the original data, 0.67 correlation, is pretty good. So we're not done yet, but I keep wanting you to like do a thing, pause, think about the thing that you did. Do another thing, pause, think about it, yeah.
Would there be like what would like a correlation that you'd be like, like this did not predict well?
I mean, it's sort of like the same as when you run any regression, right? It's if you're like the predictor variables weren't significant, the betas were low, you weren't doing much better than chance, maybe better correlation under 0.3 or 0.4 is probably like, you know, I really don't have variables in my data set that let me do much better than just guessing the mean, right? So ideally we're doing better than just guessing the mean, and if you're not, then you might as well just keep it at mean.
And recall we've been talking about, like, as far as like looking at the correlation and not like looking at the p-value of this correlation necessarily. It's like we talked about, when you have a lot of things, if there's a correlation, it's significant.
Even if it's 0.03.
Like 0.03 will be like, oh, this is super significant. It's like, really? And that's just because mathematically, when you have a huge sample, you have a tiny standard error because you're dividing by, you know, that number.
I was just gonna say what you would do if the predicted, like the correlation wasn't high, but you just said it was high.
Yeah, if it wasn't, so two things. One is we're doing a more basic imputation. There are more sophisticated methods to do imputation now through packages like mice, which the reason we're not doing it is because SPSS doesn't have that unless you pay a lot of extra money. And since I'm trying to keep the course similar to both, we're not gonna talk about that, but that's a fun, you know, near the end if we have time. Like end of semester, if we have time. For now, I just want you to sort of like think about doing something more than just getting rid of those people or just putting in the mean. So we're trying to kind of increment the sophistication of how you handle your data.
We've only got one more piece of this assignment, so if we get through it, I may speak a little bit more to like the multiple imputation thing, just at least to give kind of a verbal overview that you can look into. Because that brings us to number 24.
Well, we have to now put in the predicted values, right?
Yeah, number 24.
Perfect.
All right, so we have our predicted values. We haven't stored them anywhere or done anything with them yet, but we at least have our models and we're able to pull out those predicted values. And so now we get down to number 24 and we need to actually look at those. And specifically what we want to do is we want to look across the original values, the predicted values, and these imputed values, just those mean imputed values. No?
I think if you don't do a step in between this and what you're doing now, then we're gonna have a problem.
Oh, wait, no, it's not. It's, sorry, but let me rephrase. Your raw values, your predicted values, and the ones where you put in the predicted value for the missing values are the ones, and it's
okay.
that's where we are now.
Okay, thank you.
All right, so we need to create some variables. So as always, we're going to start out with piping into mutate to mutate and create some new variables. Just for the sake of getting all the output that I want on one thing, I'm going to mutate. I'm going to create a variable called lowercase SMA, which is literally just a copy of the uppercase SMA. Then for our predicted values, SMA predict is our predict mod SMA. So now all these values will get put in here for SMA predicted. And now we need our SMA, we need to impute those. Now for this, a very simple, straightforward way to do it, again, is using an if-else statement, where you're going to tell it, like, if it's missing, then use the value from the predicted values. If it's not missing, then just leave in the original value.
Can I pause you again for just a second? I'm really sorry, but this is really important. I don't know, maybe I keep stepping on the cord or something. And I'm going to just draw on here with this great little pen, just to be extremely excruciatingly clear about what we're doing. Let's assume...
Oh, wait, because this is on my computer, not that one.
Okay. Can you pull up a Word document for me?
Maybe.
Or if I had a dry erase marker, I would just write on the board for you.
I have a dry erase marker.
Great, then let's do that. I'll just use your dry erase. That way we can keep up the art. I'm sure it's not permanent. actually okay, I think I can just use this space right here. Okay, so we have our original SMA. Let's assume that this is our data frame. We have our predicted SMA, and that's our SMA hat, right? Predicted SMA. And now we're going to create a new variable, the SMA imputed. Okay, so let's say that this is, person number 1, 2, 3, 4, 5. And they had an SMA of 40, they had an SMA of 60, they had an SMA that was missing. Okay, so it was an NA. They had also a missing, and this person was like a high achiever and had a 95. Okay. So we have this original data already in our data frame, and because we just ran a regression, we also have these SMA predicted values, which let's say for this person they predicted a 43, and they predicted a 58, and they predicted a 41, and a 66, and a 90, okay? Obviously, we don't just want to analyze these data. I mean, if we know this person got a 40, we don't want to analyze it as a 43, okay? So what we're doing now is we're basically going to write some code that is going to tell R, if I have a value here, just copy it here, okay? So if I have something here, I'm just going to put it here. So this will just go right to there, 60 will go right to here, and 95 is going to go right to here. No problem, whatever. However, if I was originally missing a value on that variable, then pull in the number from this regression. So now I'm going to pull in 41, and I'm going to pull in 66. Okay. And just to make it even more clear, an intermediate step we took, we actually had an SMA the simple imputation, right, that we did with a mean substitution. In that column, this would have been 40, this would have been 60, this would have been, say, 50, and 50, and this would have been 95, assuming that the mean was 50. So we didn't want this, right, but we needed to run that in order to get these values. But now that we have our final one where we're actually going to use in all the rest of the analyses, if the original data were there, we want to pull it. If it wasn't there, we don't want to pull the mean, but we want to pull the regression-based best guess. And that's the step that Austin is taking now. Is that crystal clear? Mm-hmm. Yes.
And so this predicted values, just to clarify for my sake, is that we're taking other variables that are very closely related?
Yes. So in this case, our Y predicted or SMA predicted, let's actually use SMA, was a function of SRA and GPA1 because those were the most highly correlated variables we had. Okay. So that's where this number came from. These were the original data. This was the intermediate step we had so that we would actually get a predicted value. But in the end, we want to keep the original data where we can and only put in those new predicted values if we didn't have. It's better than a mean guess.
And adding in the GPA1 to the prediction just increases the predicted accuracy as opposed to just having SRA by itself?
Correct. Yes. You also saw, as you might have noticed, that there was frequently the case that if you were missing SRA, you were also missing SMA. And so if we didn't do that, we would have this weird logic loop where we'd be using the mean to predict the mean to predict the mean to predict, and so we didn't want that. So having more variables in there that increased our R, our correlate, or R squared.
Okay.
Yes,
So you
Josh.
could just add more and more if you wanted to.
You certainly could. Yeah, and you can make the strongest prediction equation that you possibly could. We could have thrown in education from parents, all kinds of other shit, but ultimately the highest, better special performing variables for us were these. This is all again for illustration. Both theory and your own data will guide what you will use. So if we had 4 variables that were all strong predictors and not redundant with each other, not super redundant, we'd have thrown them all in. Because we really just want to get our best guess here, very pragmatic. Okay, good. I wanted to make sure we're all clear about why Austin's doing this next step.
All right, so again we have, I just created a copy of our SMA, because I like all lowercase. SMA predicted is pulling out those predicted values from our models and creating that variable. Now SMA imputed, we're using this if-else. And if SMA is missing, we want to tell it, remember that if-else is always like some test, comma, output if true, comma, output if false. So if it's true that SMA is missing, we want it to output SMA predicted. If it is not missing, we want it to output SMA. So all we have to do is tell it here that if else is an A, SMA, comma, SMA predicted, comma, SMA. And now if we just run this, it's going to create those three variables, and for this imputed variable, just like she described over here, anywhere that it's not missing, it's going to put in the regular SMA value. Anywhere that it is missing, it's going to put in that imputed or that predicted value from the model. And then for SRA, you would do the same thing, but just change it all. If I can run this now, but it doesn't really help me that now it just outputs the whole data frame. So what I want to do, looking at the actual assignment, and we want to get some descriptive statistics of these variables.
And you want to assign it to the data frame, right?
Right, at some point. Okay. Well, not with the way that I'm going. I mean, yes, there, as far as carrying those variables forward, you would need to store it, but because I'm piping through to the output table, if I put that assignment, then it would screw things up. Although we could do that just to make things simple. And we'll just say, for now, I'm just going to do SMA, and so now we've created those variables in our data frame.
This might go without saying, but if you look at the last three columns of the output, that's kind of the same as what we've written on the board. So you can kind of see
Yes, yes, perfect. So you can see where exactly where the information was. So the first person there is missing SMA.
So because SMA is not missing, that's what gets put over here. Right here, SMA is missing, so instead the predicted value is put in.
Which is different from the mean value, the SRAM. Yeah. Or SMA, I'm sorry, whatever it was.
Yeah, whichever one.
SMA.
And so now we want to get the mean, standard deviations, mins, and maxes for these variables. So I'll just come here and select those new variables, SMA through SMA imputed, and pipe that into describe, which is that nice go-to descriptive statistics thing. And then from there, select to subset again to just the mean, SD, min, and max. And so now we have for our SMA, SRA, or excuse me, for our SMA predicted, the original, and the imputed ones, we have this table just as it is on the assignment. And you'll just need to go through and again, redo all this, but with SRA. But you could do, and then if you wanted to, you could take this and what would be one more step for this particular pipe right here that would make life easy? Pipe it straight into a CSV, and then you can copy and paste straight into your homework. And now it was doing that before people.
Okay.
I don't know what's going on.
I just feel like every time I stand up, it's like lightning. Okay, I also want to make another point about why we're doing this and about what it means for regression imputation, period. So your original SMA variable had a mean of 58, a little higher math achievement maybe than you might expect, since kind of on average people should be around 50, with a standard deviation of 28, and the scores range from 0 to 99. Okay, so the full range of what was possible. When we do a regression, by the very nature of regression, you can't get you can't get values that are kind of more extreme. So every time you do a regression, your predicted values are always going to be in a more narrow window. You will have reduced variance. I talked about this in class in lecture, but I'm coming back to it now. So notice that even though we have the identical mean, and this is just from our predictions, right? The standard deviation is a lot lower. We went from 28 to 17. And the reason that sort of sucks for us is because if you don't have variability in your data, then you don't have variability to explain. Meaning it's going to be really hard for any model to be significant or anything you do to be significant. If everybody's exactly the same, then nothing will predict why they're the same. So you need variability in order to be able to explain variability. As soon as we did regression imputation, we squashed the variability of scores. And you see that by the standard deviation being lower, the minimum being higher. It used to be 0, but now nobody's at 0. Everybody's at 14. And the maximum is 98 when it used to be 99. So all the scores just got truncated, which is not good. Now again, we're not using the full set of predicted values. We're only using predicted values in cases where people were missing the data. So when we go back to this new variable we created, which is like the last column here, if I had the original value, keep it. If I didn't have the original value, give me the imputed value or the predicted value. And we got a mean that was very close, a little higher, but very close. Our standard deviation is almost back up to where it was before. And our min and max is back to 0 and 99. So we've expanded the variability again, which is really good for explaining it. If it's not there, you can't explain it. Okay. In other sophisticated missing values estimation techniques, such as when you go expectation maximization, they do the same thing we did, but at this step, they just add some random shit in there. So like sometimes they'll bump someone's score up and sometimes they'll bump it down to keep variability high. So they will give a predicted value, but then they'll add a little bit of error to it in a random way. So that in the end, you have a mean and a standard deviation that are kind of like the original and a range that's like the original. So that's like the more sophisticated regression imputation. But in this case, because we didn't have that many people missing, we didn't really squash variability, which is what we need. Does that make sense, everybody? Good? Okay.
So you would consider your imputation successful if the means are similar to the original and the range is similar to the original?
Right. A successful imputation will not distort the data. Mm-hmm. It will keep the variability that you had in the original data because you still need to be able to explain it. But it will allow you now to keep the 12% of kids or whoever who are missing. So instead of throwing out 200 kids because they were sick that day or whatever, you get to keep them back in your analyses.
What if you're missing way more than that? Like we're dealing with missing around like 12, 20%, but what if you're missing like 70%? Do you still try and do this, or is that like too far of a stretch?
It could be really, really hard. First of all, if you're missing more than half of your data, it's going to be hard for you to know if there's anything systematic about it. Mm-hmm. So if you have this is where missing this relates to research design as well. So if there is, you know that the protocols you're using are too long and that people are going to miss data, for instance, you could plan for it. There are ways to plan for people to only take parts of surveys. So like we're designing a survey now that has probably 40 questionnaires. There's no fucking way one person's going to pay attention enough to do that. But we have a lot of questions we want to answer. So instead, we are randomly blocking people to take a subset of those. So like each person will take a subset of 5, but they're different subsets. So at the end, we'll be able to find our correlations and all that. You can plan for that. The biggest problem with a lot of missing data too is you can't tell if it's systematic because you've lost a lot of power. And so it's going to be, 30% of your people you're going to be looking to see whether there's anything systematic about missing this. And that's just a really low amount of power.
So like in a scenario that I'm having right now, the way that a person set up this Qualtrics account, some folks, they ask the question like, what percentage of the time are you doing this while doing this? Like being on your phone while also being on your computer. And 0% is an option, but they're selecting nothing. And so it looks like it's missing, probably they mean 0% of the time, but I can't assume that. So like I was thinking, oh, maybe this would be a way that I could assume, you know, they're probably gonna have 0, but it's probably a lot more than 30%.
So if you're in that situation, this is no longer a statistical approach, but it might be helpful. Run a pilot or a second small study where you give people the option of selecting 0 to see what happens to your distributions then. And if like it turns out that everybody who would have said 0 just skipped it, now you know, and you can maybe make some educated guesses and assumptions. Otherwise,
Design your studies based on the lowest common denominator.
Well, I didn't design it.
Oh, no, yeah, whoever designed it did a poor job.
yeah. And
Yeah,
piloting is
that's-
so important to try to catch that stuff.
That's, most of my time is spent thinking like, how are undergrads going to screw this up? What are they going to skip, and how can I deal with that? But that brings us to the end of this assignment. From there, you should be able to go back and fill in the bits that we didn't do. Does anybody have any questions? We've got like 7 minutes left.
Why did we make a copy of SMA instead of using
That's just because you can completely delete that line and just use capital SMA for these other things
He doesn't
instead.
like capitals.
I don't like capital letters in my variables.
Another reason is so you can use the colon to have it all be all the variables
Yeah,
in one line.
that puts them all together. Instead of having to say SMA, comma, then SMA predicted, and either comma or colon. In that case, I guess it doesn't really matter, except for not having to hit the space bar with extra time. But you know, it's more clear and explicit. If there's only 2, then probably shouldn't use a colon, because then it's like, wait, are there other things between these? No, just use a comma and name all 3 variables.
Can you show us the line of code where you put it into a CSV file?
Well, I didn't, but I can. What is this? It's like number 24 or something like that. So if I run that now, and then if I come over here to my working directory folder, I have a CSV that has my mean, min, max, standard deviation, etc. And then if I had already done the SRA, then piping that through, but just also have those in there. And now if you just select all these, like assuming that you have things in the right order and your variable names, then you just copy and paste these, and they'll paste directly into the table that's in Word. And then here, if I look at, let's see something real quick.
Is that the best method to do that then? You guys know get the tables into Word documents?
That's the way I do it, because like dealing with tables inside Word is the absolute bane of my existence. So anytime I'm tabling things, like I always work with it in Excel. That way I can set it how I want, merge all my cells exactly how I want. That way I have a finalized table, and all I have to do is copy and paste it into Word. Now, one thing to note, I default to CSVs just because I guess that's how I roll. But if I'm making a table, this is an important note actually, if I'm making a table that I'm wanting to, say for a publication, where now it's not just making a down and dirty table for the ease of copying and pasting it into a homework assignment, but instead I want to put it into Excel and format it, put in all my column spanners, borders, notes, all that, and like make the finalized pretty table, do not save that as a CSV. Because when you save as a CSV, it literally only saves the values that are in the cells separated by commas, in the underlying data. So you can make it as pretty as you want, all sorts of highlighting and color coding and all your italicization and bolding, all that sort of stuff. When you save it as a CSV, all of that goes away. When you open it back up, it's going to be back to just the things that are in the cells. So if it is for the purpose of making, a pretty table, you'll have to save that table as an Excel file instead of as a CSV.
And before you paste it into Word, you can, through Excel, you can decrease the number of decimals and so forth. That way your rounding is correct. That's where a lot of people, like our numbers are slightly different, is that you chop and I round, use conventional rounding. But if you use Excel or a CSV to do your rounding for you, it's not a problem.
That and you can also, write helper functions to do things for you. And for instance, this is one thing that I'll show you, but I'll caution you that it doesn't always, it works in certain cases, and so when it works versus not, you would have to pay attention to. But for instance, I wrote a helper function where in my function, the inputs are x, file, and round.to, and that's set by default to 3. And what this function does is it runs write CSV and says round x, round2 equals round, and then file, that should be, this top one should be round. And so now what it'll do is if you run this, then it gives me this function called round CSV. And notice that it asks me for my x, my file, and my round. By default it's 3. And so if I now put in some object, like if I had stored this table as an object, it'll take that object, comma, the next thing that I put into it will be the file name. So let's just say I had made a table called table. I would say table, and then name.csv. And if I do nothing else, then the default is going to round it to 3 decimal places. But if I wanted to change that, I could say, round equals 2. And now when I run this function that I created, it actually runs write CSV, but also puts in this round function so that it rounds the entire table down to 2 decimal points. So it actually exports an already rounded data frame or a table instead of 17,000 decimal places. So just pointing out that with a lot of stuff that you do in R, the ability to write real simple helper functions to do repetitive tasks makes your life infinitely easier. And so that's just one example. But anyway. Like I said, it doesn't always work perfectly. It depends on a lot of things because it can be kind of finicky depending on what input you're trying to put in, and maybe it's not actually a data frame already, or you need to convert it to a data frame before you can blah blah blah. So there's more stuff to it. I just wanted to give an example of something that you could work with as far as these, creating your own helper functions. But anyway, any other questions?
All right, so if things come up before your homework assignments due, Austin's always available, and I am rarely available, but between the two of us, we should be able to help you out.